Okay, we see example 1. Find the total flux 1 meter from a 12 nanocoulomb point charge located at the origins. How to solve this? Okay, by definition, the total flux is equal to the total charge inside the imaginary cold surface. So it's equal to 12 nanocoulomb. Okay, by definitions, the total flux equal to the charge enclosed by the closed surface. Right, next, for example 2, find the total flux on a surface of a sphere. The sphere has a uniform surface charge density of 24 nanocoulomb per meter square. The charge is 0 everywhere else. The radius of the sphere is 10 meter. Imagine you have a sphere and the charge only located on the surface of the sphere. That is the situation. So what is the flux? The flux just exactly on the surface. So the total flux equal to the total charge enclosed. And you are given the charge density. So you have to find out what is the total charge using the charge density. Therefore, you have to do the integration where the Q enclosed is equal to integration of the charge density with the surface of the sphere. And using the coordinate system that you learned in chapter 1, so we have to use the spherical coordinate. And the rho s here is a constant. So the ds here is equal to r square sine theta d theta d phi. And the radius also a constant value. So we can pull it out. The d phi is from 0 to 2 pi. And the theta is from 0 to pi. And solving this, you will get the Q enclosed equal to 6.9 microcoulomb. Next, we see example 3. From the same sphere as in example 2, find the total flux at A r equal to 5 meter from the center of the sphere. So remember our situation. You have a charge located on the surface of the sphere and the radius of the sphere is 10 meters. Now, the question asks you to find what is the total flux r equal to 5 meter from the center of the sphere. Okay, this is our sphere and our rho s is there, and we want to find at r equal to 5, which is inside our sphere. So you have to relate by definitions. Okay, the flux equal to the charge enclosed by the Gaussian surface. Therefore, in this case, the total flux is equal to total charge enclosed equal to 0. There is no charge inside this Gaussian surface because the charge is at r equal to 10. So total flux equal to 0. Okay, next. From the same sphere as in example 2, find the total flux at B r equal to 5 meter from the surface of the sphere. 5 meter from the surface of the sphere. So this is our charge system, the same charge systems. And we have to draw the Gaussian surface 5 meter from the surface. So you can predict what is the total flux. The total flux equal to Q enclosed. In this case, this Gaussian surface already enclosed all the charge system. So basically, the answer should be the same with the question A. So we have to do the same integrations where the Q enclosed equal to rho S ds. And our R here is 10, not 15, because our charge is located at R equal to 10. So R equal to 10. So we get the same answers. 9.6 microcoulomb. Even the Gaussian surface is located further away, the Q enclosed still 9.6 microcoulomb. Still the same. You have to understand the concept of the Q enclosed. Next, for example 4. An infinite line charge of 10 nanocoulomb per meter is located along x-axis. Find the total flux on a 2 meters cylinder of radius A. The axis of the cylinder is parallel to x-axis. Alright, if you are given a situation like this, you have to sketch. So you know what is this your charge system is all about. It just makes your problem solving to be easier. Okay, so your line charge is very long, infinite. Okay, and then the charge density is 10 nanocoulomb per meter. It has a uniform charge density. You have to find out what is the total flux 2 meters from a cylinder. That is the situation. So you have to sketch. This is your line charge, very long, and you take just 2 meter. Okay, you have to take just 2 meter of the line charge. Okay, and then it has the radius of A. This is your Gaussian surface. So what is the total flux? Total flux equal to Q enclosed. So only the charge enclosed by this Gaussian surface. Okay, in this case, the Gaussian surface is in the form of cylinder, not sphere. It depends on the physical behavior of your charge system. Right, so Q enclosed equal to the integration of rho L dl. So it's equal to 10 nanocoulomb multiplied by 2 meters. So it's equal to 20 nanocoulomb. So easy. The next example, using Gauss, find the electric field intensity around an infinite surface of charge distribution rho s. Now you have to find the electric field intensity around an infinite surface charge distributions. Okay, in chapter 2, we already see the expression of E field for the infinite surface charge using the Coulomb's law. Okay, the solution is quite long. Now we can see using Gauss, the solution is much simpler compared to Coulomb's law, and you will get the same expression of E field. Let's see. Let's say you have a surface, a very big surface. So basically the surface is very thin, and you take a sample of the surface. Okay, this is a sample of charge, and then you will have to analyze this sample. Right, so the sample is suitable to be solved using cylindrical coordinate. Okay, this is, we draw our Gaussian surface like this. Next, let's say the surface charge density is rho s, and our surface is S. So we have to analyze this cylinder form. So we have the top surface is equal to S1, the bottom surface equal to S2 and the side surface equal to S3. So we have the flux going up. This is equal to dz, and going down, this is a dz. Basically, there is a flux going around, but later on it will become zero. So we have to apply the closed integration of d dot ds equal to qn closed. This is our the solution from Gauss law. This is the basic expression. You have to know how to use this expression in our Gaussian surface. So you have to integrate all d into all the existing surface. In this case, we have this top surface, bottom surface, and side surface. And this is equal to the charge enclosed by the Gaussian surface, which is this part. That is the situation. So, this is how we make the solutions. First, we have the top surface, which is S1. And here we have the dz and the ds1. The integration of the top surface is ds1. Plus, we have the bottom surface, S2. The integration of dz dot ds2, the bottom surface. And we have the S3 around the cylinder. We have dr because our d in r direction going out. And then we have ds3 on the side. Is equal to q enclosed in this case is the integration of surface rho s ds. Okay, this is the surface charge. So rho s ds. Next, we expand more. So we have to know basically dz is equal to the dz and the direction of is z, the positive z. And then our surface is ds1 is going out, facing outward, so is in the z directions. And then plus the bottom surface, we have negative z directions, and we have the component of field is dz, and you have to dot product with a surface. The surface also facing downward, which is negative z, and then we have ds2. Plus we have s3, and then our d is component r, dr, and then the direction is r directions. So r, dr. And the surface is ds3. ds3 is also facing r directions. And equal to rho s ds. Since we have no component of d around the side of the cylinder, because one of the reason is, okay, the thickness of the S3 is very thin, so it's approaching zero. So that means there is no component of the side. Okay, so it's become only this Z component. Okay, refer to this figure. You can see that the S1 and S2 is basically equal to S. So we can simplify this expression into, okay, we have dz and then we have S1, because this is z dot z is equal to 1, negative z dot negative z is also equal to 1. So we have dz and ds1 equal to S1, plus here we have dz S2 equal to rho ss, and S1 equal to S2 equal to S. So we have here 2 dzs equal to rho ss, and we can cancel out the s, so we get here dz equal to rho s over 2. The magnitude of d is rho s over 2, and then we have the z component. The z component can be positive and negative z's. Let's say at z equal to 0, okay, we can define the dz into the vector d, where the d is equal to rho s over 2 in direction of z if the z is greater than 0. or D is equal to negative Z rho S over 2 if Z is less than 0. So we can say that the field D is going up and going down, depend on the location. Here we have a positive value, or positive Z direction, we have negative Z directions. So we can define lastly, the D infinite surface is equal to in direction of N rho S over 2. N is basically normal to the surface. It's going up or down. And lastly, we want to find E. E infinite surface equal to N rho S over 2 epsilon naught. So you can compare this expression with what we obtained in Coulomb's law. It should be the same. But here is much simpler approach.